So let's look at the different effects of adding interest at different times, different number of times per year. So with this example, and it's extremely fictitious, of 100% interest, investing only a dollar, for 1 year. The only thing that's not specified in our formula, A equals P times 1 plus R over N to the NT, the only thing on the right-hand side that we don't know is N, the number of times a year that interest is compounded. So for instance, if you invested your dollar on January 1st and you got 100% interest at the end of the year, 100% of a dollar is a dollar. So if you put in N equals 1 into this formula, then you're going to be left with 2. So you'll have $2 at the end of the year. Okay. Well, let's try it compounding twice a year. That is semi-annually. So you invest a dollar on January 1. Then halfway through the year, they give you half of the interest. So 50% of a dollar is 50 cents. Now that's added to your account. And the cool thing is that at the end of the year, you get interest on your interest. So if you get the remaining 50% interest, 50% of $1.50 is what? 75 cents. 75 cents added to your $1.50. Now you got $2.25. So that's kind of cool. As you compound more often, you get more money. So then you say, hey, I like this game. Let's play it a lot. You compound quarterly. Now you get back $2.44 roughly. Or monthly, $2.61. And then what the bank considers daily is 360, and you get $2.71 back. But you notice something. It's kind of slowing down a little bit, right? I mean, we went from twice a year to 4 times a year, we got an extra 19 cents. From 4 to 12, we got an extra 17 cents. From 12 to 360, we only got an extra dime. Can anyone suggest, if this is sort of daily, how often would this be? How often are you compounding down here? Hourly, yeah. So if you wanted to, you could compound hourly. And look at that. Going from 360 to 8,760, you're not even getting an extra half a penny. All right, it's just making the smallest of difference. So using calculus, you can actually put in, effectively, infinity. Compound infinitely often. And this is exactly how much you would get. Now, other than the number pi, E is the most important natural constant that you're going to run into. And it's actually programmed on your calculator. You can find it in a couple places. So let's take a look at it on the graphing calculator. On the graphing calculator, you can find it in 2 places. It's right above the division sign. So how would you get that to print out on your calculator? Second and then division sign will give you E. And you should be able to get that. Now, on all of your calculators, regardless if it's a graphing calculator or not, you should be able to find it in another place, and that's right above the ln key. So hit the second key, then the ln key. The difference here is that it's going to expect an exponent. So let's just put it to the first power and do e to the first power, and you should get exactly what we got just a minute ago. Since we're here, why don't we practice e to the second power as well? So second ln, e to the second power, basically e squared, something like that. Is everyone able to get e off their calculator? E and powers of e? Because e, boy, e is a special number. Comes up in a ton of places. And it occurred naturally first in working with compound interest. So if you're going to compound interest continuously, then we've got a different formula. You might have noticed it on your exam. It wasn't a problem that I assigned on the exam, but I had the formula there. A equals P e to the RT. This is the formula for continuously compounded interest. So right here. So if your bank's telling you, yeah, we're going to compound interest continuously, that's great. This is the formula that they're going to be using. So let's practice with that a little bit. and try and get comfortable with the number e. Thank you, squared. Okay. All right, so sorry, gotta get my wits about me again. All right, so from yeah, I did. I mean, they're on the wall someplace. I have to get the janitor to help me out. Let's play around with e a little bit, and no comment. Let's do a comparison. Problem number 76 asks us to compare a couple things. You know, interest compounded kind of like the regular way, and then compare it to continuously compounded interest. So problem number 76. This is initial positive $30,000 grows at a rate of 8% for 20 years. So P is 30,000. The rate is 8%. And right away, let's just write that as a decimal, 0.08. And the time is 30 years. Now, what they want you to do is compare final balance resulting from annual compounding and continuous compounding. So there should be kind of a big difference. If you're compounding annually, what are they telling you about n? No, kind of n's 1. Annually, once a year. So annually is n equals 1. Plugging that in, our formula is going to look like this one, filled in. It's going to be A equals 30,000 times 1 plus 1 over 1 to the n, which is 1 times 30. No, excuse me. I was looking at that going, wait a minute, that's going to be a 2 there. No. Yeah, it needs to be a 0.08 up here. 0.08 divided by 1 raised to the 30th, 1 times 30 power. Let's see how that's going to pan out. Basically, in here you get 1 plus 0.08 or 1.08. So it's going to be 30,000 times 1.08 raised to the 30th power. So about $301,879.71. Again, round your money problems to the nearest penny. It's about 301,879.71. But what if I try to calculate this again, except this time using continuously compounded interest? I think it's going to make a substantial difference. So here you get 30,000 e to the 0.08 times 30, like that. So let's calculate this. Now, we have to type in the 30,000 first. If when you hit the second key and the ln key, if it gives you e to some power, like that, then you need to type in a left parenthesis 0.08 times 30. If not, then you're lucky, your calculator's up to date. You just type in 0.08 times 30 up in the exponent. But if you get this little caret, then you got to use the parentheses here. So 0.08 times 30. So did it make a nice difference? Yeah, I'd say it's worth driving a little extra ways to get the continuously compounded interest. Let's take a look here. You should end up with approximately 330,695.29. So roughly $29,000 more with continuously compounded interest as opposed to what I tend to call simple interest. So here's one, there's the other. The big thing here, though, is to get used to the key for E. Are we okay with those two calculations? You know, again, the formula for continuously compounded interest, this right here is something that I would give to you on an exam. It's not something I expect you to remember. But one thing you do have to know is when to use which formula. If they're telling you interest is compounded 3 times a year, 4 times a year, 5, 12, hourly, whatever, they're giving you N. You want to be using this formula right here. If they don't give you N, if N is kind of implied because you have continuously compounded interest, then you're going to be using this formula. In this formula, N is built into that constant E. Okay?
The first part, I didn't know N was 1.
They told you that interest was compounded annually. So it'd be once a year. Semi-annually would be twice a year, quarterly, 4, monthly, 12. So, and then daily is 360, but I would remind you that daily is 360. Because it always amused me about that. Anything else on problem number 76?
And you wanted which was you had put on there like which was the better investment.
Right. So I just
on there that third part which is the better investment.
yeah. So on previous exams, I've given problems like this, and I say, well, which is the better investment? Really, what I expect is you to calculate both of them, and then just say, okay, well, this one's the better one. Typically, what I would do is I would adjust the interest rates and the rate of compounding so that they're close, so that you can't really tell. I mean, this one, with a little bit of experience, you can probably look at that and say, well, continuously compound is going to do a lot better.
Right.
But on an exam, I'd adjust them so that they would be close. Basically, so you'd have to calculate them out. Okay? All right, appreciate the question. Let's try one kind of in an opposite direction of that one. It's problem number 38. Here they tell you that let's see. Well, let's see. Maybe it's not the opposite direction. P is 39,000 or 33,999. R is negative 4%. And T is 21 years. Negative 4% is kind of interesting. What that means is that this asset's going to be depreciating. So you can think of it as maybe a car that you buy or a computer that you buy, although that number would probably be a bigger negative number. But let's put that into our formula. They give it to you, A equals P e to the RT. They used to make a shampoo called Pert. Oh, do they still make it? Yeah? Okay. Yeah? Do you use it?
No, my dad does. I was gonna say my dad uses it. It's like a guy shampoo.
Yeah. Nah, I don't use it. Sorry. So let's see. 33,999 e to the negative. What should I put here? Negative what?
0.04.
Good. 0.04 times 21. Now, because it's negative, you're going to get a decay. So you're going to start out with more than you end up with. See if you can't get that number out of your calculator. And let's see, where should we round this? Round to the nearest hundredth per the instructions. Well, it's 4%. So 4% as a decimal is 0.04. And then the negative came with it. Okay, so less than half of what you started out with after 21 years. So about 14,677.73. Are you able to get that off your calculator? Is that a number that you can get without too much sweat? Yeah? Okay. Okay, well, if you're comfortable with E, then let me introduce something else. Now, on your exam, one of the problems you had was log of x equals something, some negative number like negative 2.34 or something like that. And somebody asked me a question about it. So, well, what's the base? And I said, well, the base is implied. I can't really tell you. But now that the test is over, what's the base? 10. All right, good. The base is understood to be 10. Now, there's another special base of a logarithm, and when the logarithm has a base of e. So when the logarithm has a base of e, and you saw it on the exam, it's abbreviated ln x. Of course, I threw those problems out because we hadn't covered that yet, but log base e it's called the natural log of x. So this is a natural log. And if you wanted some terminology for this, not that people use it very much, but this is called the common log. So you have the common log and the natural log. So both of these are notations that are supposed to be understood. Log base 10 of x, we'll just write that as log of x. And log base e of x is ln of x. Now, other than like an intro example, you're not going to see the books write log base e of x. Hardly at all. I like to write it a lot because I think it's a little less abstract, and this helps us do some cancellation work with logarithms that you might not see otherwise. So for instance, problem number 42, they give you ln of e squared. Well, that's really the same thing as the log base e of e squared. Now you might ask, well, why make a fuss like that? And the reason I would suggest that we do this is because when you have the log of a base and that base to a certain power, those two operations cancel each other out. So these two things just cancel and give me 2. That's kind of cool. Let's check it out. Let's check it out this way. Let's calculate e squared on our calculator. And now let's take the natural log of that. So how do you take the natural log of something? Well, you hit the ln key. Now notice your calculator actually does give you kind of a nice reminder here. Take a look what's right above the log key. Log 10 to the x. ln of x, e to the x. So that tells you exactly what's going on here. Now if I want to take the log of that number, that previous number, I'll hit the ln key, and then I'll hit the second key, and then the minus key. It's going to take the log of my previous answer. But what should I get when I press that enter key? 2. So the log of e squared is 2. Those two operations cancel each other out. That's kind of cool. Now we'll actually practice a few in a minute where we're not going to get cancellation. The idea is just to get some decimal values. But let's try problem number 44. And maybe you can kind of anticipate me on this one. ln of e to the 4th. Norman? basically, again, these operations cancel each other out. The logarithm, the exponential functions are inverse functions of each other. That's how we introduce the log, is saying, oh, gee, it's an inverse. We can keep on going. There's a bunch of examples like this. Let's do a couple just strict calculations, and maybe we'll come back and do one more like this. Problem number 54. Just to get used to the ln key. ln of 0.675. I'm going to round this to 4 decimal places. So, okay, just a straightforward calculation. ln of 0.675. So here's the number I get. I get negative 0.39304, etc. If I round that to the 4th decimal place, do I need to put the 0 there? If you're asked to round to the 4th decimal place, do I need to put the 0 there? Yes. There better be something, because right now it looks like you've rounded to the 3rd decimal place, doesn't it? So if you put a 0 there, even though it doesn't change the value of that, it's now rounded to the nearest 10,000th, not to the nearest thousandth. Let's try 2 more. Problem number 58. ln of 2.7, and problem number 60, ln of negative 10. So again, just looking for some decimal answers here. Colin, what'd you get for the first one? All right, so if we rounded that to the nearest 10,000th, what would it be? 3. Good. Is everyone getting those numbers? Lisa? Getting those? Okay. Mila? All right. How about log of negative 10? What'd you get there? Anyone? A non-real answer? Desmos. Well, let's take a look at things. Do you remember the graph of the log of x? No, we haven't done the graphs of the log yet. So, well, let's start out this way. Y equals, say, 2 to the x is that graph. Now, when I try and find its inverse, I have x equals 2 to the y. That's that graph. Let's make those a little bit darker. Thank you. So the second graph, the blue one, is a graph of your logarithm. And I can play that same game with base e. So let's change these up from base 2 to base e. Now there's not a real big difference between base e and base 2. That difference is highlighted on your sheet here. So let's take a look at that before I change it up on the graph. Whoops, I don't want that one. I want this one down here. So on your handout, one of these is 2 to the x, one of them is e to the x. Is there a big difference between these two functions? Same general form, right? They both pass through 0, 1. They both have a horizontal asymptote at y equals 0. They both grow really, really quickly, except which one do you think is 2 to the x and which one do you think is e to the x? I'll call this A and B. Which one do you think is 2 to the x? Which one do you think is e to the x? A is 2 to the x and B is the other one, e to the x? Okay. Well, let's keep in mind one thing about e. E is about 2.718. So it's going to be a bigger number. When you raise a bigger number to the same power, you're going to get a bigger number. So if you look, for instance, at what happens when x equals 1. When x equals 1, 1 to the 2 power is 2. When x equals 1, 1 to the 2.7 power is up here. 1 to the 2.718 power. So this first one is y equals e to the x, and this one is y equals 2 to the x. But they have the same general shape to them. Now I remark about the shape because I want to look at the shape of the graph of e to the x and the graph of its inverse. Here's both graphs. And in particular, the second one was really kind of a disguise. It's the graph of y equals a log of x, the ln of x. So here's that graph. Do you think this graph goes to the left of the y-axis? Does it extend anywhere for x less than or equal to 0? No. And that's the problem that you're running into with the log here. So when you try to take the natural log of 10, or negative 10, you ran into a problem. It's outside of the area where this is actually defined. So this one for us, let's see if they ask you to write something in particular, if possible. All right, so let's just write does not exist. All right, you can't do that. Technically speaking, this is outside the domain. Let's do one more with our log function here, and that would be problem number, let's see, problem number 46. So let's go back to 46. ln of 1 over e squared. Close. To get this out of the denominator, I'll have to rewrite that as the ln of e to the negative 2. Oh, is it a cube? All right. We'll tell you what. This is problem 46-ish, which is the way the author really intended to write it, but they made a typo. So ln, yeah, absolutely. ln of e to the negative second. Dylan, take a shot at that one. You could also rewrite it as log base e of e to the negative second, and then log base e of e to the negative, yeah, negative 2. So again, just like problems 42 and 44, these two operations cancel each other out because the log and the exponential function are inverses of each other. Okay, let's practice a couple more problems with exponential functions. So I had one I was going to do, but in the wake of things over the weekend, I'm going to change that one. Let's take a look at world population growth. So problem number 80. This is actually one of your homework problems. So population of Earth is approximately 6.8 billion people. No, that's not true. It's about 7.4 right now. So let's do 7.4 billion. And it's growing at a rate of about 1.133% per year. So R equals 1.133%. Let's convert that right away to a decimal. 0.01133. And we want to know what the population is going to be like in, say, 30 years. So t equals 30. The model for this exponential growth, a very simple model, maybe not very realistic, but a very simple model. What's that? I know, but that's old. If you Google this today, this morning, you'd see it's about 7.4 billion. We passed we passed the 7 billion mark in like March of 2012. It's amazing that we've already added 400 million people to the world. That's just wow. That's a lot of people. Yeah, you're right. Thank you. Yeah, VP. So the question is, what's the population going to be like in 30 years? So that would be A equals 7.4 e to the 0.01133 times 30. Round your answer here to the nearest tenth. I don't think this formula is going to be that accurate that we need to round it to, the nearest 10,000th. So what kind of answers are you getting? About 10.4 billion? 10.4 billion. That's a lot of people. Man, get your lakefront property now. It's going to get crowded. Let's kind of change pace a little bit and try a problem like number 62. In fact, I think problem number 68, or one like it was on your exam. Let's take a look at 62. 62 is ln of x equals positive 2.6490. Now, as I said earlier, the author is not going to be in the habit of writing things as log base e. The author is just going to write ln of x. I find it more convenient in a problem like this to write it as log base e. Why? Why would that help me out? Well, it helps me out because I can rewrite this now using exponents. Kennedy, what would this look like if I rewrote this using exponents? Perfect. So this is equivalent to e to the 2.6490 equals x. So all I have to do is do e to that power. And that's a feature that's even built into your calculator. So second function, ln, e to the 2.649, about 14.13989, etc. for x. Here again, they want you to round to the nearest 10,000th place. So to the nearest 10,000th place, 14.1399 for x. By the way, if you're looking at that going, that's just such a strange number, I don't trust it. How could I check that? Yeah. If you take the log of that, you should get exactly this. Now, this is really convenient, especially if you have a graphing calculator. You can take the log of your previous answer just by hitting the ln key, then the second button, and then the inverse key down here. And that'll take the log of your previous answer, and you get exactly 2.649. Yay. So it worked. Now, if you typed in the approximation, if I did ln of 14.1399, Am I going to get exactly 2.649? No. You should get close though, right? We're pretty close. I say really close. So again, it's reassuring. If you forget this trick of your previous answer, then you can just do it kind of manually. Nothing wrong with that. So in looking at this and thinking about your old exam or the exam you had today, one of the problems I crossed off was actually number 67 right out of your book. So let's try problem number 66. You try problem 66. Ln of x equals negative 0.28. So do two things. Find it and check it. All right. Everyone good on that? Should get about 0.7 something. So this can be rewritten using exponents. That's really log base e of x equals negative 0.0 or negative 0.28. There's no decimal there. E to the negative 0.28. Second e to the negative 0.28. About 0.7558. So about 0.7558. Okay. Let's play around with the graphs of E for a little bit. Are we okay with manipulating some of these equations, working with E so far? So the graphs of E, we commented earlier that the graph of e to the x is not too much different than the graph of 3 to the x or the graph of 2 to the x. So let's play with a few of these, starting with problem number 30. And what I have on your paper here for you is y equals e to the x. And in comparison, we want to graph y equals e to the x minus 5. Now this should cause a familiar shift. How is this graph going to be shifted compared to our graph of y equals e to the x? Yeah, to the right 5. So there's one point on these graphs that I really want you to make sure you graph correctly. What is it? Yeah. So the point here at 0, 1 in our new graph is going to be over here at 5 and 1. So basically you're going to draw as best you can this graph shifted over here. So let me just pull this down for a second. Do my best to draw that graph. Not too bad. So when I grade your exams, the point that I'll be looking to see will be this one. Our new point here at 5 and 1, where the graph has been shifted to. And that's pretty much it. It's just understanding the translation. It's the same idea that we did earlier. Yes, sir. Well, because this point is at 0 and 1. That's the only point that I really know on this graph. Any other point that you come up with is going to be pretty difficult. I mean, like even at x equal 1, you're at 2.71828, etc. It's not a nice friendly number. So this is the only point that I was worried about. The graph gets shifted to the right by 5. So that point got shifted to the right by 5. Anything else in problem number 30? Let's try problem number 28. F of x is e to the x minus 2. How's this one going to be shifted? Down by 2. So a couple things here. First of all, we have a horizontal asymptote at the line y equals 0. Where's that new horizontal asymptote going to be? Yeah, at negative 2. So down here. And the asymptote is certainly something that I would want to see. Y equals negative 2. How about the point at 0, 1? Where should I draw that one in my new graph? Lisa? No, I've already picked on you today. Gil. That would be shifting it down 3. There you go. So at negative 1. So shifting it down 2. And then again, just drawing this same graph, shifted down 2. So something more or less like that. So the two things I'd be looking for on a graph of this function, one would be the correct horizontal asymptote. That got shifted down by 2. And the second thing is this. I guess the third thing is that, at least a decent general shape. There is a tendency sometimes for people to, go kind of overboard in avoiding this, and they'll bounce off of it like a pool table. Like they ricochet off of it. Like, no, it keeps on getting close. If you accidentally touch it, that's fine. I'm not going to worry about it. The only thing that I don't want you to do is just egregiously cross it. It does not cross that line. A couple more on this one. Problem number 26. Y equals e to the negative e to the x. What do you think that negative is going to do to our graph? Flip it upside down. So instead of having a point at 0, 1, we'll have a point at 0, negative 1. Instead of having something that shoots up towards positive infinity, we're going to have something that shoots down towards negative infinity. So something roughly like that. Not perfect, but I think you get the general idea. And let's do one more last example, kind of a combo example. Y equals It's my own example. It's not one that's in the book. The one that's in the book, it's not one that I was assigned. They have y equals 2e to the x, or y equals 1/2 times e to the x. What putting a number in front of this is going to do is it's going to stretch the graph away from the x-axis. But we're not working with those kinds of shifts really all that much, so I'm going to kind of skip on that part. So let's do e to the x plus 2 minus 3. So a couple shifts in this one. See if you can't figure out where the new horizontal asymptote is, and also figure out roughly where this point is going to be in our new graph. Okay. So which way is this graph going to get shifted? Kenzie?
Down 3 and left 2.
Down 3 and left 2. Good. So where does that mean our new horizontal asymptote is? All right, thank you. So y equals -3. That's our new horizontal asymptote. The graph should not go below that at all. Down 2, excuse me, to the left 2 and down 3, that should put this point at -2 and -2. How would I find the y-intercept if I wanted to? I don't necessarily have to on a problem like this. Not what I'm looking for, but set x to 0. So if I set x equal to 0, I get e to the 0 plus 2 minus 3, which is e squared minus 3. E squared, I think we calculated earlier when we calculated e for the first time. We got 7.2 or 3 something, 7.2 something. Let's see. What would that be? E squared. 7.38. So 7.38 minus 3 is going to be 4.38. So maybe about there if we wanted to be very careful. On a problem like this, it's not my first concern. I want to see y equals -3, and I want to see the point at -2 and 2, and a pretty decently drawn graph. Am I making myself clear about what I expect from these graphs? Okay. Then let me give you some homework. For homework, try 25 through 29, 33 through 47, 53 through 67, 75, and 99. And that's section 11.5.